So when thinking about the periodic table, the most underlining concept of why we have periodicity in the periodic table is Coulombic attraction. So let's think about, why does sodium act like potassium? Last class we talked about the organization of the periodic table. We know that it's based off from the atomic number. We know that everybody in the same group has the same number of valence electrons, and that those valence electrons are what give them their specific properties. We know that if you're in the same group, you have similar properties because you have the same number of valence electrons. So why does sodium act like potassium? Because they both share one valence electron, both found in group 1. So what's Coulombic attraction? Coulombic attraction is the attraction between a positive charge and negatively charged particle. In this case, what we're talking about is protons and electrons. Conversely, we know that two charges of the same type are going to repel each other. That's going to be a key point when we talk about ions in a little bit. So key idea number one. Key idea number one says the closer two opposite charges are, the stronger the attraction. Just the opposite. If you're far away, you're going to have less attraction. So think about magnets. The closer magnets are, the stronger the attraction. The farther away, the weaker the attraction. So you can see as you go from A to B to C, as you increase that distance, you're going to lose that attraction. This is talking about distance. Think about parts on the atom. When we talk about distance, we're talking about principal energy levels. Key idea number two, more positive charges. So more protons exert a stronger attractive force than less positive charges. So you can see as I go from 1 proton to 2 to 3 to 4, that force of attraction is going to increase. So the more protons you have, the stronger the force. And then the last part kind of ties it together, but electrons are attracted to the nucleus. These act as the attraction points, all right here, as long as they are at equal distance. So the electrons are attracted to the nucleus. This attraction depends on how many protons there are and the distance. So this depends on the count of the protons, but also the principal energy levels. How many principal energy levels do you have? If you have a lot of principal energy levels, that attraction is going to be weaker on the outer electrons than on the inner electrons. They experience repulsive forces from each other. So we have two forces going on here. We have the attraction, but we also have the repulsion. So we have to keep both charges in mind when we talk about key idea number 3. So Coulombic forces of attraction between the positive and negative particles. So as you head across the period, Coulombic attraction increases because your atomic radius decreases. We're going to talk about atomic radius in a second. But really, let's focus on the number of protons. Number of protons increases and the number of valence electrons increases. I have more points to be attracted to because I have more valence electrons. And I have more protons, which means I have a stronger force. Remember, force is based off of protons. I would like to say the hooking or pulling in of is based off from the electrons. So I have more strength, more places to hook into, draws that radius in shorter. And this is what, again, reiterates that distance because the radius is going to be even smaller. Think about fluorine. Okay, fluorine only has 2 principal energy levels. Distance is small, has 7 valence electrons, 7 places to hook into with a small distance, going to have quite a bit of attraction. As you go down a group, Coulombic attraction decreases because the atomic radius increases. Remember, when we talk about radius, we're going to talk about that distance, and we refer back to principal energy levels. So I have more principal energy levels. I go from 1 to 2 to 3 to 4 to 5 to 6 to 7 principal energy levels. As I increase the number of principal energy levels, this causes those electrons to be farther. And like we said for key idea number 1, the farther you are, the less attraction. So now our nucleus is decreasing in attraction. Just to kind of reiterate, when you're looking at the periodic table, you move across the period. I'm going from left to right, move across that row. Number of principal energy levels stays the same. If I'm in period 1, I have 1. 2, I have 2, 3, and so on. However, my number of protons is increasing. My number is going up. I go from 3 to 4 to 5 to 6 to 7 to 8 to 9. Okay, so I have more protons. I have more valence electrons. So the number of valence electrons increases, therefore increases my attraction. Remember, there's 2 things going on here. Nuclear force because of the number of protons, but also what I like to call the electron hook. They're hooking these and dragging them in, hooking these and dragging them in. You can only attract to the opposite charge. If you don't have those charges available, you can't draw them in. The more that you have to draw in, the smaller that radii is going to get. So the four big terms for this unit is going to be atomic radius, which is the distance of the nucleus to the outermost electron, just like in math class. You're going from the center of the circle to the outside of the circle. For us, it's the valence shell. Metallic character really is how easily an element loses an electron. This is really what deals with reactivity. Ionization energy is the energy required to remove the outermost electron. So I want to take away an electron. And just the opposite is the attraction, okay, or the gaining of electrons. So these are just the opposites. If electronegativity goes up, the energy required to remove one goes up. Okay, if the stronger the attraction, the harder it is to pull away that electron. These two go hand in hand. Okay, and we're going to actually talk about these two. The larger the radius, the easier it is for an element to lose. So these are direct, and these are both direct. So I like to talk about atomic radius and metallic character together. And I like to talk about ionization and electronegativity together. You remember one, you remember the other. And the nice part about this is radius can be found on table S, and both ionization energy and electronegativity can be found on table S. So atomic radius, the distance from the nucleus to the valence shell. As you go across the period, it decreases because Columbic attraction increases. Again, why does the attraction increase? You have more protons and more electrons in the valence shell. More places to hook into to drag them towards the nucleus, and stronger nuclei. As you go down a group, what happens? We know our atomic radius increases. Why is that? Because the number of principal energy levels increases. Distance. This one's all about distance. Okay? Principal energy levels causes a greater distance. Therefore, bigger radius. As you go from left to right, why does your radius get smaller? Well, you're hooking more electrons, drawing them in towards the nucleus. So metallic characteristics. Okay, so how much an atom acts like a metal, how easily it loses an electron. So we're looking at loss of electrons. We know metals don't like to have their electrons typically. It's easier for them to get rid of them than to gain them. We have our semi-metals, which act a little bit different. We would have some specific instances, but we're just talking general. So as you move across the period, okay, it decreases. You're heading towards the non-metals. If you're going from left to right, you're going to decrease in metallic characteristics. Remember, our non-metals are found over here, per se. That's where we're going. If we're going over there, these ones want to gain electrons. They don't want to lose electrons because they're closer to group 18, that 8 full valence electrons in the outermost shell. As you move down a group, your metallic characteristics are going to increase. Why? It's easier for an electron with a bigger atom to lose an electron. Okay, so easier to lose an electron if the atom is bigger. Okay, think of that force. The farther away you are, the harder it is for me to hook into that electron. Most metallic elements are in the lower left corner. Okay, so francium is the metal of the metal. That is what every metal wants to be like, even though it doesn't really exist for very long periods of time, if at all, unless given specific instances. But that's the big focus point. Okay, so metallic characteristic is going against the backwards thinking of Coulombic forces of attraction. You don't want to be attracted to your nucleus if you're a metal. Ionization energy. Okay, ionization energy is the energy to remove the outermost. So how much energy do I have to take or put into the system to take out an electron? As you go across the period, you know your ionization energy is going to increase. We just got done talking about it. I have more protons. I have more electrons to hook into and to drag towards me for attraction. Not going to be very easy to pull away electrons that are strongly attracted to the nuclei. Then as you go down a group, we know our ionization energy is going to decrease. As it decreases, why? Because you gain more principal energy levels. Easiest one. Far away. If they're far away, it's not very hard for one to be taken away because they're not that strongly attracted towards the nuclei. So when we talk about ions, we have two types of ions. We have positive ions, which we call cations. We have negative ions, which are A-negative ions, called anions. Cations lose an electron, which means that they reduce the electron cloud. Think of lithium. Lithium has a 2-1 configuration. It gets rid of the outermost electron. It lost the whole principal energy level, so its radius got smaller. Most metals will lose all of their valence electrons. Therefore, when they lose those valence electrons, they lose the whole principal energy level. Their radius gets smaller. When we look at anions, we know anions like to gain electrons. They like to bring in that extra electron to complete their valence shell. Well, as they bring in electrons, what do electrons do to one another? Well, they repel. And as they repel, they get farther away, which causes their radii to get larger. So kind of relationship to cations and anions, we talk about electronegativity. Okay, electronegativity is your ability to attract an electron. You want a strong attraction. So as you go from left to right, your electronegativity is going to increase. They want electrons. Okay, remember, all halogens just want one more electron. Well, what other things affect your ability to attract electrons? Also, your size. Okay, so how far away from the nucleus are you? But also that relative to the number of protons in your nuclei. So as you go down a group, your electronegativity is going to decrease. Think they want to get rid of their electrons. Francium has the largest radius. Since it has the largest radius, it's not very difficult to pull away that outermost electron. Since it's not very difficult to pull away that outermost electron, your electronegativity is very low. Do you ever get confused for electronegativity? Where did I say you could find this? On table S. All the values for every element are on table S. So to summarize, like I talked about earlier on, okay, we talked about electronegativity and ionization energy. Okay, increase in ionization energy, I have an increase in electronegativity. If I have an increase in atomic radius, I have an increase in metallic characteristic. You can see that these two concepts travel together, and these two travel together. Atomic radius, you can find on table S. Electronegativity and ionization energy, you can find on table S. There's no reason to get these trends wrong, because that means you didn't look at table S. I would strongly consider, if you don't remember these, you don't memorize these, you can compare two elements of the same period, and you can compare two elements of the same group. So from that trend, you should see electronegativity and ionization energy increases up and to the right, and atomic radius and metallic characteristics increase down and to the left. So that's periodic table. Why the periodic table has periodicity, how it is arranged, who developed it, and some of the easy ways to see trends and predict behavior of elements based off from just the table alone.